Looking at section 4 now, so continuing on with these tests, we have two so far. We have the nth term test and we have the integral test. Remember, all these tests are as ways for us to see whether a series converges or diverges. The next set of tests we're going to be looking at are comparison tests, and there's two different ones. There's just the generic comparison test, which we have as the theorem. So what this one says, let there be three sequences, A sub n, C sub n, and D sub n. I don't know why they skip B, they just do. We'll see why in a second, actually. B series with non-negative terms. Suppose that for some n, we have the following inequality, that the series, well, not the series, sorry, just the sequence values themselves, that always we have D sub n is less than or equal to A sub n is less than or equal to C sub n for all little n greater than this index value capital M. Okay, great. So all this is saying so far is this kind of like the setup to the squeeze theorem that we had back in section 1 for sequences. So it's similar, just a little bit different here. I don't know why this didn't index. There it goes. Just a little bit different for series. So if we have this as a setup, then there's two different parts that we can say. If we have that the series C sub n converges, then we automatically get that the series A sub n also converges. So let's stop and talk about this one a little bit before we write down number 2. If we always have two sequence values where one of them is always smaller than another one after a certain index value, then as we go to infinity, this has to go to 0 very quickly, which means this also has to go to 0 even quicker. So if we know that the bigger values converge, then we automatically get that smaller values would also have to add up to be converging in a series. 2 is very similar, just the other way around. So what 2 says is that if D sub n diverges, then we also have to have that anything bigger than that diverges. Oh, geez, sorry. I need to just tear that button off of my keyboard. So same thing. If we have two sequences where one of them is smaller than the other, if the smaller one diverges, then anything bigger than that would also have to diverge. Let's look at a couple of examples of using this. I will say that this comparison test here is not one that we are going to use a lot moving forward, mainly because it's difficult to find sequences to use. We will use it some, though. So here's an example of using one. So here we have the sequence 5 over 5n minus 1. And we just want to know, does this converge or diverge? Okay. I would go through all of the tests first, right? So we have the nth term test. The nth term test is going to be inconclusive because we have the denominator blows up to infinity, which means the whole thing goes to 0, so inconclusive there. Then we have the integral test. With the integral test, we have to have a bunch of different prerequisites. They have to always be positive. They have to be decreasing. And they have to form a continuous function. I actually think that you could do the integral test for this one and it would work out just fine. But let's not do that one this time. Let's do the comparison test. When you're using the comparison test, what you want to do is you want to find another series where the sequence values are always bigger than this after a certain location or always smaller than this, something that you know either diverges or converges. That is why this comparison test is kind of difficult, because unless you have one in mind, it can be a little bit hard. There is kind of a tip to picking out what the other series is going to be. You want to pick out a series that behaves very similarly to the series that you already have. If this -1 wasn't here, then this would behave very closely to just 1 over n because the 5's would cancel out. Whenever you have just a constant value that's added or subtracted in the numerator or the denominator, you can kind of ignore it, because once this n gets very large, this -1's not doing anything anyway. So what we're going to do is we're going to use another series, just the series 1 over n. We know this diverges. We know this diverges because this is just the harmonic series, or you can think of it like the p series where the exponent is 1. Okay. So what we need to know is we need to know how the comparison works between 1 over n and 5 over 5n minus 1. Is this a less than sign? Is that a greater than sign? To do that, you could look at the two functions' graphs and pick that out, or you could just plug in values for n to see which way it's going to go. And remember that it has to be big orders of n. It can't just be 1, 2, 3, because it can be one way to start off with. Just remember for the definition here, it's eventually this has to be the inequality that holds for these two outcomes here. So just plugging in big values for n and kind of playing around with it a little bit, you should find that 1 over n is always less than or equal to 5 over 5n minus 1. What that means is that we have part 2 of our definition perfectly. We have that this series, 1 over n, diverges, and this divergent series is less than a series that we don't really know what happens. Thus, by the comparison test, we have the series, the one that we started off with up there, the 5 over 5n minus 1, as the n goes to infinity, must diverge. Cool. All right, let's look at one more example of this comparison test. Let's look at the series n equals 1 to infinity of 1 over n factorial. All right, so we haven't messed around with factorials too much at this point. I did define it a few videos ago. If you're unsure of what a factorial is, just Google it to see how that works. But we want to figure out if this thing converges or diverges. And this one, we definitely could not use the integral test because we can't integrate over these factorials. So we have to use a comparison test. So does this converge or diverge? Okay, so again, we have to pick out another series that's either always bigger than this that converges or is always less than this that diverges. And this is what I mean by it's kind of hard to pick something like that out without already having a pretty good knowledge of things that converge or diverge. For this instance, we're going to use this series, 1 over 2 to the n. This is a geometric series, right? You can take that n out and make this just 1/2 to the n, and we know that this converges. This converges since it is a geometric series with r equal to 1/2. Okay. Since this converges, we need to figure out which way the inequality is going to go between 1 over n factorial and then 1 over 2 to the n. We hope that 1 over 2 to the n is always going to be bigger than 1 over n factorial. That way we get that this converges by the comparison test up above. So again, just plug in big values of n. You can do factorials in the calculator, so just to pull up the calculator real quick. Let's say we're picking n to be, we can't go too big because the calculator freaks out. Let's just do like n to be maybe 10. So 1 over 10 factorial, so we're going to do 1 over 10, and then to get to factorial, you're going to go to math, and then over to, I think it's probability, and then there it is, the number 4 option here. So math, arrow over to probability, and then 4. 1 over 10 factorial is a super tiny number. Let's compare that with 1 over 2 to the 10 power. Okay, so this only has 4 decimal places. This one has 7 decimal places, which means this one is the bigger number. So 1 over 2 to the n is always going to be bigger than 1 over 10 factorial, which means my inequality is going to go this way. Oh, sorry, I just did it backwards. That way, right? 1 over 2 to the n is bigger than 1 over n factorial. Okay, and then that's all we need. Thus, by the comparison test, we have that the series 1 over n factorial converges. It converges because we found a series that is bigger than it that we know converges. So therefore, the smaller thing, 1 over n factorial, also has to converge. Okay, cool. So that's the normal comparison test. In the next video, we're going to look at the other kind of comparison test.